much of a taste we develop for this stuff. Okay. So again, electricity generation, AC, and then DC, solar produces DC, and then also, as we've talked about, batteries. So when you put a battery into a device, that's also a DC source. Okay. Any questions on that?
What's the best way to turn the crank?
What's the best way? Well,
Yeah,
there's always
not from a cost perspective. Just like without using like coal and stuff like that. Just water. You think water, wind?
Well, there's always a trade-off, right?
Yeah.
There's an environmental impact.
Yeah.
There is a greenhouse gases trade-off. You know, there's a what do you do with your nuclear fuel thing? There's always some kind of trade-off. And it's interesting to go into that, and when you actually get into the science of what's better or worse, a lot of the times the science and the policy actually are different. So, but there's no easy answer, right? The big thing that they want, the holy grail, is nuclear fusion, which will be both clean and plentiful, but no one can seem to figure out how to really get that going on a mass scale. Okay, so the last order of business is messing around a little bit more with the n term, the number of loops. Now, n has entered into our equation simply as, hey, let's make it as big as possible to accentuate the effect, but we haven't really messed with it. That's what we're going to do next. And that's something called electric transformer. When you have those black power cubes you plug in, that's basically a transformer. Let's talk about what that's all about. So an electric transformer. So here's what an electric transformer is. It is one coil of wire. Now you're going to have to imagine that that wire has insulation on it, because I'm about to do something that may make you think that these are somehow electrically related. I'm going to take another coil and just going to interlace it. Now these aren't electrically connected. There's insulation around both wires, so they kind of wrap around each other, but there's no way for any given electron to flow from one to the other. They just share the same space. We actually named the two, these are two independent circuits. We call this the primary circuit, P for short, and we call this the secondary circuit. Okay? So the only thing that relates them is that they both have coils, and the coils share the same actual physical space in their interior. So this interior space is actually shared by both. So let's see what we can do with this. What we're going to do is we're going to send current through the primary. So that's the input. So you might question if the secondary is going to do anything if it's not electrically connected, but it does. Okay. Oh, and I guess I should mention that the input current is driven by some input EMF, right? So I apply some EMF at the primary. That EMF is going to drive the current. You can't get current unless you apply an EMF. Okay. All right. So let me take my Lenz's law, or sorry, my Faraday's law, and I'm going to go ahead and write it like this. So here what's going to happen is that the EMF is going to be the input, but of course the EMF is going to drive current in that primary coil, and that creates a magnetic flux through the core. So this is kind of like the output. if I apply an EMF here, I'll send a current through the solenoid, and that solenoid, of course, if you send a current through it, it'll create a magnetic field through the middle. So I guess I can draw that. It might look something like this. So that causes a flux change in that core. And the way that I'm going to write this output is like this. I'm going to factor out the number of loops and then characterize this as the flux change per loop. So flux change per loop times number of loops gets me back the entire flux change, right? All right? Well, this is when we see what the utility is of having these two solenoids share the same space, because the flux that is made by the primary will get caught by the secondary. Okay? So if we go over to the secondary, then this is the input, whoops, right? That flux that's being sent by the primary is being caught by the secondary. That's the input, and then the result is that we will have induced EMF and induced current on the output side. So even though these are not electrically connected, the fact that one can send flux and the other can catch it, well, we can have something over here. This is induced EMF and induced current. So we will have that there is induced current in some direction, induced current in the secondary. The two completely not electrically connected circuits are actually communicating through shared flux. And once again, I might characterize this as flux change per loop times the number of loops. Now at this stage, if it's not already painfully obvious, the input is going to have to change all the time in order for there to be an output, right? So the input is actually going to have to be AC. The current has to slosh back and forth all the time. It has to have some kind of change so that the flux made through the primary isn't static. Because remember, flux caught by the secondary is not sufficient. It has to change all the time. Flux is not sufficient. You have to change with time. So you're going to have to make some kind of change all the time in your input side so that the flux caught by the secondary changes all the time. That's where your induced stuff comes from, right? In fact, if you always change this to fight the flux change will always be changing. This is your output. So that's what you have. AC goes in, AC comes out. Now you might say, what is the point of this thing? If you wanted AC, just use the primary. Okay, just connect whatever you want to apply AC current to the primary. What's the point of the secondary? Well, let's take a look. Our assumption is going to be that because these two things share the same space, the flux sent by one loop is exactly caught by another loop. These two things are the same. Okay? So these are the same. Sent equals caught. That's what we have. So to give you an illustration of that, I can draw one turn of the primary, which might look like this. That's one turn of the primary. And this is one turn of the secondary, which is basically right next to it. And whatever is made by one is effectively immediately caught by the other. I guess let's go ahead and do an example. Let's say that the current at this moment, I don't know, let's say that the current inputted into the primary looks like that. So which way is the magnetic field going to be roughly through the center? Up. So this is the B that's sent by that's made by the primary. So this is kind of B in. I guess I can call it B sent. Okay. Here's a question, a trick question. Which way does B induced point? Trick question. You need to know something else, don't you? What's the missing piece of information? You can't say. Well, we know B external, the B sent, that's the external as far as the secondary is concerned. But what else do we have to know before we know the direction of B induced? It's increasing or decreasing, that's right. Right? Remember there's flux change to be thought. So we don't know if the current is increasing or decreasing. Let's say that it's decreasing. So B sent is decreasing at this moment because the current is decreasing. So the I primary is decreasing at this moment. Remember, that is going to be an AC source, so the current is going to always be changing. It's not constant. You can see the problem now. If the primary current was constant and B sent was constant, then nothing would happen in the secondary, right? You need change. Okay, so if it's decreasing at this moment, which way does B induced point? Same way, right? Do one that points the same way on occasion so that you don't always think they're opposite. So B induced is like this. And so which way would the induced current in the secondary be at this moment? This way, right? So this right here would be I in the secondary at this moment. Okay? So there what we have is a situation where we've been able to do the play-by-play of Lenz's law. Of course, what you're going to have is that if you're constantly sloshing the current back and forth, in the primary, there's always something that the secondary induced current will be, right? And we're assuming, though, that this flux sent and the flux caught by the secondary is one and the same flux, right? They're sharing the same space. So this being sent is also the external field that gets caught by the other ring and induces the other one, right? So flux change per time is really important, but we're just about to eliminate it from the equation, okay, because it's common. So let me go ahead and solve. I get this. So don't forget, even though we just eliminated the flux change per time from the equation as the common variable, if the flux change per time were 0, we'd get nothing, okay? So what do we have? We have the E in the secondary, if that's our desire to find it. The EMF induced in the secondary is not quite exactly the EMF that was sent in the primary. The difference is that you get to multiply by the ratio of the total number in the secondary and in the primary, okay? So this right here is the extra little trickery we have to what we say is transform the way that the electricity is transported. You're not going to get exactly the same thing in the secondary as you have in the primary. If that's all you wanted to do, then what's the whole point of this thing? We actually are going to transform the energy. So I'm not going to be able to finish that today, but it won't take too many minutes next week. You have a couple options. You have what's called, I guess we can call that the number of secondary loops is greater than the number of primary loops. Okay? You have more catchers and less senders in total. Okay? So let's make a sketch of that. Now, oftentimes, just to make it easier to count loops, we kind of take the coils apart just so we can see. This would look like this. So we have that, here are the senders, the primaries, and then I'll draw many more catchers on the secondary side. Okay? That just allows us to visually see that there's more catchers on the secondary side than senders on the primary. Remember, I'm doing this with the primary on the right, on the left, and the secondary on the right. So what are we going to have? According to the equation, the ratio in front here is going to be bigger than 1. We have that the EMF seen in the secondary is greater than the EMF seen in the primary. We have increased the voltage. We call this a step-up transformer because it's stepping up the voltage. So when you hear step up or step down, it's relative to the EMF. You're stepping it up. Of course, the opposite case, what if you have less catchers in the secondary and more senders in the primary? That would look like this. More senders, less catchers. Then your EMF in your secondary is less than in your primary. We call this a step down. We've lost voltage. So, what's going on here? Well, I want to remind you that the units of voltage in general is joules per coulomb, right? Volts or joules per coulomb or energy per charge. Okay? Seems weird. The step up especially. We get more energy per charge out of the secondary than we sent into the primary. It seems like we're getting something for nothing, right? It seems like we're conjuring up more energy. If we get more voltage out of the secondary than we sent into the primary. Well, of course, that can't happen. You just can't conjure up energy. There is something in the denominator that has to give. All I'm saying is there's more energy per charge. Well, if the number of charges changes, then you haven't violated any energy conservation, right? So here, we're getting more energy per charge on the output. Over here, of course, we're getting less energy per charge on the output. Now there you might say, where'd the energy go? Well, this is a little bit more palatable. You can say, oh, it went to resistance or something, right? Well, there's no resistance in here either. So you should be concerned where the energy go. Okay? In both cases, you didn't conjure up energy out of nothing. You didn't send it into nothing. The energy's all still there. Okay? We're going to examine next time that just because you transform the energy per charge, the energy's all still there. It looks like I'm out of time, so let's pick that up next time.